Similar to the price feed, these two addresses are going to change based on the blockchain that we're on. So it'll probably make sense for us to parameterize them the same way we parameterize the price feed address. So in our top level constructor parameters, we'll add an address for the VRF coordinator, and we'll pass this to the constructor of our VRF consumer base. Then we'll also grab an address for the link token. So we'll do address link, and we'll pass this to the VRF consumer base constructor as well. Great. What else do we need to make this work? Well, back in the documentation, we can see we need a fee and a key hash. The fee is associated with the link token needed to pay for this request. So we'll make a public variable, uint256 public fee. Since this might change blockchain to blockchain, we'll have this as an input parameter as well. So we'll do uint256 underscore fee. And in our constructor, we'll do fee equals underscore fee. We'll set our global variable to fee. And I need a comma here and no semicolon here. What else do we need? Well, we need a key hash. The key hash is a way to uniquely identify the Chainlink VRF node. So we'll create another one. We'll do bytes32 public key hash. We'll add this as a parameter in here. Bytes32 key hash. And then we'll say key hash equals underscore key hash. Perfect. Our contract is coming along great here. Now that we have the main pieces that we need, how do we then request this random number? Well, if we scroll down in the documentation, we can see we have this request randomness function that we need to call. If we scroll back to our VRF consumer base contract, this request randomness function is a built-in function from the VRF consumer base. So our contract can natively call this request randomness function right in our contract. And you can see it takes a key hash and a fee as its parameters. So right in our end lottery function, we can add this function. And we can see this also returns a bytes32 called request ID. This return syntax is pretty powerful. You can actually identify the name of the variable you want to return right in your function declaration. So by saying bytes32 request ID, we're saying we're going to return a bytes32 variable named request ID. So right in our function here, we can do request randomness, because again, that's this function that we're importing, passing it the key hash and the fee. This will return a bytes32 called request ID. So this is actually doing this and having our function declaration tell us that there's going to be a variable named request ID is going to be exactly the same as if we did bytes32 request ID equals request randomness. Now, this function call follows, again, what we've talked about as the request and receive mentality, the request and receive architecture. This means that in this first transaction, we're going to request the data from the Chainlink Oracle. In a second callback transaction, the Chainlink node is going to return the data to this contract into another function called fulfill randomness. So again, if we look back in our VRF consumer base, we can see it has this function raw fulfill randomness. We can read some of the comments in here saying raw fulfill randomness is called by a VRF coordinator when it receives a valid VRF proof. Raw fulfill randomness will then call fulfill randomness. So there's a little bit of contract tag going on, but it's going to eventually call this fulfill randomness function, which is going to be what we define in here. And that's how our contract is going to know what to do once it gets the random number back. So in our first transaction, we're going to end the lottery, request a random number, and then in a second transaction later on, once the Chainlink node has created a provably random number, it's going to call a second transaction itself based off of what we define. We just have to call it fulfill randomness. And as you can see, it takes a byte32 request ID and a random number. So in here, we'll do fulfill randomness, takes a byte32 request ID, and then a uint256 randomness. We don't want anyone else to be able to call this function. We only want our chain link node to call this function so we can return a truly random number. So we're going to make this an internal function. It's internal because actually the chain link node is calling the VRF coordinator, and then the VRF coordinator is calling our fulfill randomness. So we'll make this internal so that only the VRF coordinator can be the one to call and return this function. And then we're going to give it a keyword of override. This override keyword means that we're overriding the original declaration of the fulfill randomness function. Our VRF consumer base has a function fulfill randomness defined, but it doesn't have any parameters or anything about this function actually laid out. This function is meant to be overridden by us, and that's exactly what we're doing right here. So in this fulfill randomness function, let's go ahead and define what's going to happen once we get this random number back. So before we can process this random number, let's just check to make sure we're even in the right state. So we'll do require. Our lottery state is going to be equal to lottery state dot calculating winner. And if we're not in that state, we'll just say you aren't there yet. My auto format is on for this one, so it's jumping in. Then let's just do another check to make sure we actually get a response. So we'll do require underscore randomness is greater than 0. And if it's not, we'll just say random not found. Now we need to pick a random winner. Well, we need to pick a random winner specifically out of our list of players, our list of payable public players. So our players array is just a list of players. So it's like player 1, player 2, player 3, player 4, and they're each at a different index. What we can do then to pick a random winner is to do what's called a modulo function. In fact, let's even open Remix to do an example of this. Remix, let's pop open a new contract. We'll call it mod.sol. We'll do pragma solidity caret 0.6.6. We'll do contract mod. And in here, we'll do a constructor, blank constructor, and we'll get a global variable, uint256, number, and we'll set it equal to 5. And we'll go down to 0.6.6. We'll save, compile, and let's even just get rid of the constructor. Let's now create a function called doMod. We'll take a uint256 mod value, make this a public function. Public view returns uint256, and we'll just return 5 modulo mod value. Now let's go to JavaScript VM. We'll deploy this. We'll go in here. So our number is right now 5, and let's learn about how the modulo works. If we have this doMod function, what we're doing is the module divides by the number and returns the remainder. For example, if we did 5 mod 5, what do you think we're going to get? So we're going to do 5 divided by 5 and then return the remainder. Well, 5 divided by 5 is 1, and there's no remainder. There's no decimal there. So 5 mod 5 should be what? 0, exactly. Well, what's 5 mod 4 then? Well, 4 can go into 5 evenly once, but there's one number left over. So 5 mod 4 is going to be 1. 5 mod 3 is going to be 2. 5 mod 1 is going to be 0, right? Since 1 goes with everything. This is how the mod function works, and it's this little percent here. We can use that mod function in our fulfill randomness with the length of our players. So we can say uint256 index of winner is going to be equal to the random number that we got modded by the players dot length. So let's say, for example, we had 7 players sign up and our random number was 22. Well, we want to get one of these random 7 players. So we would do 22 mod 7. 7 divides evenly into 22 3 times, with 1 left over. 7 times 3 equals 21. Difference between 21 and 22 is 1. 7 times 4 is 28. So we know, this is how we know we've reached our upper limit. So this is how we can get a random number based off of the index. Now that we have this index, what we can do is we can say the winner equals players of the index of winner. And just to keep track, let's make a new variable called recent winner at the top. We'll do address public recent winner. We'll grab this recent winner. Instead of winner, we'll say recent winner equals players in this index of winner here. Now that we've got a winner, well, we want to pay them all of the money gathered from our enters here. So what we can do is we'll do this recent winner dot transfer the entire balance of this address. So we'll say address of this dot balance, and perfect. We'll transfer them everything that we have. Then of course, we're going to want to reset the lottery so that we can start from scratch. We can start blank again. So we'll do players equals new address payable array of size 0. So we're just resetting players to just be a brand new array. Then we're going to change our lottery state to being lottery state.closed because the lottery is now complete. And I often also like to keep track of the most recent random number. So at the top, I'll do a uint256 public randomness variable. And in our fulfill randomness, I'll say randomness now equals underscore randomness. And perfect, we now have a contract here. Of course, we haven't actually tried it out, but we're assuming that it works great. So you know what this means. It's time to go into testing mode, testing and development mode. But let's even just try to do a brownie compile first. Looks like we have an issue here. Send and transfer are only available for objects of type address payable, not address. Oops. Looks like we made our recent winner just an address, but it needs to be an address payable. So let's try brownie compile again. And beautiful, we at least know it's compiling, so that's a great sign. Let's now move into our testing and development phase. As you are starting to figure out, we can ignore these file import callback not supported bugs in VS Code for now. I'm sure the Solidity linter will get better as time progresses. But great, so now let's go ahead and move into actually testing and working with everything here. So let's go ahead into our scripts, and we'll make a little deploy script first. Let's do a new file. We'll call it deploy lottery.py, and let's go ahead and deploy our lottery. So same as always, we'll do def main. We'll come up with a new function called deploy lottery, and then we'll do def deploy lottery, and then we'll just have a pass for now. And if we run this, brownie runs scripts, deploy lottery.py. Our default network is not defined, which means the default is going to be development. We can even be verbose here, development, write that in our brownie config. Run this, a ganache will get spun up, and nothing will happen because our deploy lottery function doesn't do anything right now. Awesome. The first thing we need always to deploy a contract is we need an account. So we'll do account equals, and we've been using this get account function for some time that we've been adding in a helpful script section so that it can pull from a real testnet or from a local development environment if we like. So to do this, of course, let's create our new helpful scripts.py. We'll create our init__py so that Python recognizes it as a package. And in here, we'll create a new function, def get account. now we'll just have it pass.